Okay, what we're going to start with is kind of a summary of a little bit about what we discussed last time. And we have this idea of a fundamental connection for polynomial functions. This is one of the boxes in your book here. Ultimately, if we have a polynomial function f, okay, and a real number k, the following statements are equivalent. Okay, so number one is if x equals k is a solution or a root of the equation f of x equals 0. Okay, so keep in mind that that all four of these are going to be true at the same time. So if number one is true, that means number two is also true, which means 3 is true, which means 4 is true, etc. So as long as we know one of these four things is a fact, okay, then the rest of them are all facts as well. So when we have the equation f of x equals 0, okay, we say that the number that makes that true, or keep in mind it could be the numbers, there could be more than one answer, of course. Okay, the numbers that make that true, which we'll call k, okay, then we call those solutions or roots. Okay, the term 0 is used when we say that k is a 0 of the function f. Okay, it's a solution to the equation. It's a 0 of the function. In the third one, okay, graphically we say that k is an x-intercept of the graph of f of x. Okay. And then finally, if we know that any of that is true, then we also know that x minus k is a factor of f of x. Okay. So a little bit about this is vocabulary. We want to make sure that when we're talking about answers that make the equation equal to 0, okay, we call those solutions or roots. Okay. If we're talking about the function itself, then we say that if we know this number, okay, makes the function equal 0, then we call it a 0. And again, we also know that recognizing that on a graph is recognizing the x-intercepts as those k values. And then also if we were to factor f of x, okay, we know that x minus k would be a factor. Okay. Now, let's take a look at the next theorem here, because if you remember on the last time we met, I talked about the fact that if we had just a random cubic function, or quartic function, or anything higher than 2, essentially, okay, unless I had something I could factor out, like factor out an x, and get down to a linear and a quadratic, okay, I might not be able to just look at it and know what to do in terms of factoring. Okay, if I have something of higher degree than 2. Well, the first thing that we could try, and I mentioned it on the last time, was that if we graphed the function, looked at it on our calculator, we might be able to see that, yeah, it looks like it goes through at x equals 3. So 3 might be a possible 0 for the function. Okay, and if that's the case, then we can try synthetic division, and we can divide it by 3 and see if, yeah, it actually is a 0. All right. Now, if the zeros that we looked at on the calculator, if the x-intercepts did not look like they went through whole numbers, though, okay, then that wouldn't be terribly helpful, then, would it? Okay, unless they go through a whole number, then the calculator is not going to help much. Okay, so what we have next then is this what we call the rational zeros theorem. Okay, so bottom line is we have this polynomial. It's got degree greater than or equal to 1. Okay, it's of the normal polynomial form. Okay, with every coefficient an integer. So keep in mind that these numbers in front have to be integers, otherwise this is not going to work. Okay, so we're going to have those numbers in front be integers. Okay, and the a sub 0 cannot equal 0. Okay, keep in mind if a sub 0 equals 0, then each of the terms would have an x, and then we could just factor out the x. Okay, so keeping in mind this has to be, there has to be a constant term, if you will. And what it boils down to is that if x equals p over q, okay, is a rational 0 of f, where p and q have no common integer factors other than 1, okay, then this gp is an integer factor of the coefficient a sub 0, and g of q is a factor of the leading coefficient. Now, that notation is rather confusing as far as I'm concerned. Okay, so let's talk about that in much simpler terms. Okay, what does all that mean? Okay, what it means is that we're going to look at these two terms. We're going to look at a sub 0, and we're going to look at a sub n. A sub 0 being the constant term, a sub n being the leading coefficient. Fair enough? And what we're going to do is we're going to make a list of what we call possible rational zeros. Okay, so possible rational zeros. Okay, they have to come from factors of the constant term divided by factors of the leading coefficient. Okay, so this list has to come from factors of this one divided by factors of this one. And this is pretty powerful because what we're saying is this: if there are rational zeros, keep in mind rational being ones that can be written as fractions, okay, nice ones if you will. Okay, a number is pretty nice if you can write it as a fraction. If it were a irrational number like radical 3, that's not very nice because the decimal doesn't ever repeat or terminate. Okay, fractions are generally nice numbers. So if we have any rational zeros, okay, they have to be of the form factors of this over factors of this. Okay, so let's see that in action. I'm going to go back to this lower bound test in just a minute, but ultimately this would be a problem that we might be asked to tackle here. We have 2x to the 5th minus x to the 4th, etc., and we want to find all real zeros of this. Okay, and then we want to identify them as rational or irrational. Okay, so what we want to do here first is we're going to make a list of the possible rational zeros. Okay, so what I'm going to do then is I'm going to make a list of the factors of the constant. Okay, so that's going to be 1 and 36, 2 and 18, 3 and 12, 4 and 6, not 4 and 6, 4 and 9 that is, and then finally 6. Okay? And we don't need to write 6 and 6, we can just write 6, that's just one factor. Okay, that's going to be our list of factors for the constant term. The leading term only has 2 factors, just 2 and 1. Okay, so if we make that list, okay, those are going to be our list of factors. Now, for us, what we're going to have to check then is we're going to have to check all combinations of the constant term factors divided by the leading coefficient factors. So I'm going to put a line underneath these, and then I'm going to make the list from what I have right here. So I'm going to start with a 1. Watch how I make this list, because this is what you're going to do in a minute. We're going to start with 1, we're going to put it over 2, and we're going to put it over 1. And in fact, I'm going to actually put these in numerical order here, and I'm going to count these in numerical order also. So I'm going to go 1 over 1. Okay, that's going to give me 1. I'm going to go 1 over 2. That's going to give me a half. Okay, and they don't. When you write this list out, it doesn't necessarily have to be in the exact order or numerical, smallest to lowest. Okay, and if we do our, I'm going to go ahead and do my 2 next. I'm going to start with the lowest one here. So I got 2 over 1 and 2 over 2. So 2 over 1 would give me a 2. 2 over 2 would give me a 1, but I already have 1 on the list, so I'm not going to write that again. It's already in the list. Okay. Then I'm going to go to 3. I have 3 over 1. And then 3 over 2, that's not in the list yet, so I'll put that in my list. Okay. Then I'll go to my 4 over 1 and 4 over 2. 4 over 1 needs to be added, but 4 over 2 is 2, which I already have in the list. Then I go to my 6 over 1. 6 over 2 is 3, so I already got that in the list. I don't need to add that. Okay. And then I go to my next smallest one will be the 9, because I got 4 and 9 here in my list. So 9 over 1 and 9 over 2 would have to get added to the list. Okay. All right. And then I'd go to my next largest one, which is 12. It'd be 12 over 1. 12 over 2 would be 6, which I already have. Then I have an 18. And an 18 over 2 is 9, which I already have. And then I have a 36 over 1, which is 36. And 36 over 2 is 18, which I already have. All right. Now, so what I've done is I've narrowed this down to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got 12 different possible rational roots here. Okay. Now, one thing that is not good for us, though, is that we have 12, but really we have 24, because it could be the negatives of any of those also. Okay. Because remember, factors of 36, I could have negative 4 times negative 9, and those two would be factors also, wouldn't they? Okay. So I got to consider the negatives of all these. Now, here's the good news. Okay. When I want to do division here, okay, I only have to check these 24, okay, which is good because how many rational numbers are there? Okay. How many rational numbers are there in general? There's an infinite amount. Okay, so 24 is better than infinity. True? Okay, so would I even have to check 5 at this point? Would I try to divide this by 5 and see if it works? No, because 5 is not even an option. Okay, if there are rational roots, okay, then they have to be from this list that we just created. Okay. Now, what I could do here next, okay, and if this were on a calculator test, this is what I would do next. I would look at my graph now and see if any of these look like they might be answers here. Okay, so let's go ahead and do that. Brandon, get the lights for me. So if I go ahead and put my 2x to the 5th in, minus x to the 4th, minus 2x cubed minus 14x squared minus 6x plus 36. And if I do zoom 6 on that, I'm not sure how much of that we'll see, if any. Okay, we know it's possible that there could be zeros that are pretty big here, but we can see that there's 1, 2, 3 right in front of us. Okay, keeping in mind that this is a 5th degree function. Okay, it could be that these are the only ones. That's possible. Okay, could be that these are the only ones. Okay, remember also it could be, since this is 5th degree. Okay, keep in mind that if this is 5th degree though, and this goes down here, okay, if it were to come back up, okay, it wouldn't have the right end behavior, would it? Okay, for a 5th degree function. Same thing here. If this one were to come back down at some point, okay, it would have to go back up, wouldn't it? Could it be possible that it goes up, down, and then back up and be okay? Sure. Or it could do that same thing on the other side too. Keeping in mind that positive and negative 36 are the biggest rational roots we can get if we wanted to do our window, say to negative 40 to 40, just to check to see if we see anything else. Okay, we might still just see those 3. Okay, it looks like there's nothing else on there. So we'd have pretty good reason to believe at this point that those are the only 3 real roots here. And if I zoom back in to my standard window, it looks like it goes through maybe negative 1.5 here, maybe. Also, it looks like maybe it goes through 1.5 and then maybe 2 over here. So 2 might be a good candidate. Okay, I would also take a look at my table at this point. If I put my table set on, let's say, negative 10, and go by 1s, or let's go by 0.5s, because then maybe some of these halves or 1.5s or whatnot might be zeros. So if we look at our values here, of course, we're getting closer to 0 as we approach. And look at that right there. We can see that negative 1.5 is a 0, which is in our list. That's that one right there, the negative version. Okay. And if we go over to 2, remember I said 1.5, but it turns out 1.5 is not. True. But it looks like 2 is. Fair enough. Okay. All right. Now, remember the question here is find all the real zeros. Well, I know what 2 of them are from there, but I want to make sure I can find the rest. So here's what I'm going to do next. Okay, so based on that, I'm going to take my number, set up my synthetic division. Okay, and I'm going to use negative 3/2 because I am pretty sure that that's one of the answers based on my work from the calculator. So I'm going to try to prove that that's true by using my division process. So we'll bring down our 2. And if I multiply, I'm going to get negative 3. If I add those 2, I'm going to get negative 4. Multiply these 2, I'm going to get 6. Add those, I'm going to get 4. Multiply, I'm going to get negative 6. Add, that's going to give me negative 20. I'm going to multiply these 2 together, and that's going to give me negative 30. Nope, positive 30, sorry. Add those 2 and give me 24. And when I multiply those 2 together, it gives me negative 36. And sure enough, we do get a 0 remainder. Okay. Now, remember what that does for us is a couple things. Number 1, it tells us one of the zeros. And remember, we're looking for 5 total. Okay, there's a maximum of 5 real zeros here. Okay. Not only does it do that, though, but it also gives us the quartic remainder. Okay, so now we went from a quintic equation down to a quartic equation. Fair enough. Okay. And now here's the nice part about the synthetic division is we could divide this by 2 also and show that the remainder is 0. Okay. But the equation that we're left over here with, since it's quartic, okay, we can just take that and do another division. Okay, with the other one that we know is the answer, which we, again, from the calculator, we know that 2 is going to work. Okay, and what's nice is that we can take the quartic that we got from the remainder part, we can divide that because when we do that, we're going to end up with a cubic. So each time we divide, we can divide it by the remainder part, okay, and we're going to break it down into smaller and smaller parts. So let's see if that works in this case. So I'm going to bring down my 2. I'm going to multiply and add. 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 and sure enough I get a 0 remainder there. Okay. Alright. Now remember though that what I have left here is 2x cubed. There's no squared term, plus 4x minus 12. Okay, that's what this remainder equation is in this particular case. Alright. And the other issue is, okay, does this have any other zeros? Okay, Lydia, question?
Yeah, how do you normally divide by 2?
Okay. So remember in the calculator we looked earlier that 2 was also a 0? Okay. So we thought that went through there at 0. Okay. Now, the question is, what do we do with this? Because right now we have 2 of the real zeros. True? Okay. And remember from the calculator, if you look at the graph again, okay, it looks like it's got to be somewhere between 1 and 2 is the other one. The other real one that we can see. Now, if you look back at our list up here, okay, if you look at this one, this is the only one that's between 1 and 2, isn't it? Okay. There are no other numbers here that are between 1 and 2. Okay, and we know the answer is not 3 halves. We could divide it by 3 halves and see that the remainder is not 0 and rule that one out. Okay, so if it's not in the list, okay, then what do we do? Well, like I said, we have 2 of them right here already. Okay, to find the third one, if it's not in the list of rational zeros, then it's got to be irrational. Okay, so our only choice at this point then would be to use the calculator and use the 0 command. Okay, and we know how to do that. So that other one that we're trying to find, that third one, okay, we would have no choice but to use the 0 command. Okay. And the other part of this would be that this particular one that we started with, okay, we wouldn't be able to completely factor this because the 0 that we would find would be irrational, okay, which means that we wouldn't be able to write it as a factor unless we rounded it. So we could get approximations for it, okay, but we'd have to settle for a decimal for that third one. Okay. Questions so far?